Hi everybody, thanks for giving me the opportunity to present on the topics of application I/O profiling on HPC. My name is Melvin So. I've been working at the High Performance Computing Center at the Nanyang Technological University, NTU in short, for over 16 years. And I can say I truly enjoy my work at the pace of change in this field. It's very fast and it suits the curious and restless person like myself. I understand that most of our participants here are already working in the HPC AI field in one way or another. So another hi to fellow HPC folks. I hope my presentation will facilitate some conversation, if not curiosity and interest in the area of application I/O profiling. Let me move to my first slide. Now, a little bit about my organization I work in. Nanyang Technological University, NTU in short, is a research-intensive public university, supporting about 33,000 undergraduate and postgraduate students in the engineering, science, business and humanity, art, social science, and medicine. And that's not all. We have about 10,000 faculty, researchers, and administrative staff, and more than 265,000 alumni. NTU is sited in the western part of Singapore. One prominent characteristic of NTU, besides its strong international academic standing, it is its beauty and greenness. The university main campus at Nanyang Avenue is frequently listed among the top 15 most beautiful campuses in the world. The university also holds the national record in 2019 of 57 Green Mark certified building projects. You can see from the photos that green is a frequent color in the university. If you're in Singapore for a visit, please feel free to come to NTU and take a look and capture a few photographs. The High Performance Computing Center was established in 2010 to support the need of large-scale and compute and data-intensive computation at the university. For more than 10 years, we have grown and achieved recognition for energy, efficiency, pioneering technology, and innovation. Located on the north spine of NTU, HPCC provides resources, services, and expertise to NTU research community. With more than 4,500 CPU core, 40 NVIDIA Tesla GPU card, 2,700 terabytes of storage, 100 gigabyte of InfiniBand, and 40G/100G Ethernet backbone supported by a small team of 4 HPC engineers, including myself. HPC have churned out about 90 million core CPU hours and nearly 300,000 GPU hours annually to support more than 160 research groups at NTU. Our HPC digital community has also grown to nearly 800 NTU members, and their contributions are critical. As the HPC user and community grow, the number of HPC AI applications and the scale of computation grow exponentially as well. We are a small team of 4 engineers. We seriously needed a cutting-edge tool to provide more insights and intelligence into our operation. Now, at the job level, we needed to understand runtime issue with greater clarity. We needed to detect work job and bad I/O patterns so that problematic application can be addressed. We needed metrics on I/O, CPU, and memory to identify bottlenecks. Now, with the insight, we want to translate the information we have gathered for informed business intelligence. We can determine the most affordable and best fitted performance, storage, and node for the type of application. We can also determine the right place and the right resources. We can facilitate the groundwork for hybrid cloud environment by using the metric we have gathered and identify the applications suited for the cloud and what run best on the premise. We just installed Mistral 3 weeks back, and we wanted to find some useful information and insight quickly on the characteristic of that application. The application of choice is our computational chemistry software, Gaussian G16C. Gaussian is an electronic structure program used widely by chemists, chemical engineers, biochemists, and other scientists worldwide. The number of cores used for the job is 16 cores per job only, and we allow the job to run for approximately 12 hours. We dispatch the job to the same server for the test, and the specification of the server is as follows: dual socket, CPU Intel Xeon Go 6150 CPU Skylake with 768 GB RAM and Zen OS 7.6. Using Altair PBS Professional and Altair Mistral, we submitted the job into the node and captured it run. Here are some of its characteristics. Right, from the Altair Mistral, we observe that there's heavy read-write operation for small files, 4 KB, and large file, 1 megabyte and above. The read-write operation for 32 to 1 megabyte is not significant. Here again from the Mistral, we can see that in terms of read and write, there's a lot of space used by the file larger than 2 megabytes. Although there are lots of read and write operation for the smaller file, it is not significant in terms of byte use. For mid-size file, the size taken is almost negligible. So what is the general characteristic of latency for the application? Okay. From the start of the application till the last 2 hours, the mean latency for the various file sizes are fairly consistent. But at the last 2 hours, there is a spike in the I/O operations, as well as read and large write operations. Right? The I/O bandwidth for the application is fairly consistent at around 4 GB and spiking at the last 3 hours, especially at the last hour. Even for a fairly small short application, the demand is still around 4 GB. Imagine if we decide to use a 1 GB network, the application will throttle badly even though the compute node may be very good. Now the application used fairly small memory footprint, at least for this particular job. I also understand that Gaussian can be configured to consume more memory to improve performance if required, but we must configure it at the input file level. Now, there are 6 important parameters to determine the job characteristic and performance. Using the Altair Mistral, we were able to take a look at read and write count, read and write bytes, memory usage, processing time, latency time, and bandwidth usage. Now, with the information gathered, we start to have a better insight of what is happening and what we should take note for Gaussian applications. Now, for the next phase of the profiling, we wanted to test the interaction of the Gaussian application with 3 production storage at HPCC. We wanted to know what is the performance metric for this different tier of storage for Gaussian. Now, I just want to put a caveat that this test case can only be used as an observation and not a conclusion, as the storage subsystems are in production and intensively used at varying degree. They are not fully isolated for this test run only. So at HPCC, we have 3 basic types of storage. We have the scale-out all-flash NAS, right? For applications that require fast write and intense metadata operation, but mounted on NFS v3. We also have the scale-out NAS with lots of SSD and hard disk to act as L3 cache and read and write, and hard disk for tiering mounted with MNS v3. We also have the local drive that require ultra-low latency with direct write to disk for scratch. Now, we ran the same application as a job solely on each of the storage subsystem sequentially to get performance metrics relevant to the storage. These are observations. Now, the first parameter is MetaOps mean latency, right? The mean latency, right, of local NVMe and scale-out all-flash NAS is very good at 0.001 milliseconds. The latency latency for scale-out NAS was higher at 0.002 millisecond, which is 2 times more latency. The meta highest value should be always related to the mean value, right? A larger gap between the mean and the highest value mean a less consistent performance for that period recorded. Again, the meta ops high value for local NVMe was fantastic at 0.014 milliseconds. The scale-out all-flash NAS was at 3.41 milliseconds, and the scale-out NAS was at 0.459 milliseconds. From here, we can see the local NVMe has the best meta ops, and the scale-out NAS is the slowest. The next parameter we look at is the read mean latency. The mean latency for read for all three storage, 32 KB and smaller, was at 0.002 milliseconds. The mean latency for medium read is separating the three storage apart with the scale-out NAS having the lowest latency at 0.109 milliseconds, followed by NVMe, and finally the scale-out all-flash NAS. The mean latency for large read is led by the scale-out NAS at 0.009 milliseconds. The scale all-flash NAS came in second with 0.015 milliseconds, and finally the local NVMe at 0.018 milliseconds. Okay, for read latency, right, as mentioned, a higher gap between the mean and the highest value mean a less consistent performer for that period recorded. Now for the small read latency, the local NVMe led the pack with 0.462 milliseconds, followed by the scale-out NAS, and finally the scale-out all-flash NAS. The scale-out for medium read latency, right, the scale-out NAS with its huge cache led the way with 5.447 milliseconds, followed by the all-flash NAS and local NVMe. For large read latency, the scale-out NAS again led the pack with 123.99 milliseconds, faster than the local NVMe, but the scale-out all-flash NAS is the largest at 308.969 milliseconds. I'm not sure why the huge gap. It definitely warrants further investigation. Now, one thing we can conclude and one thing we can see is that when we come to read latency operation, a good scale-out NAS with lots of DIMM and L3 cache can perform very well and hold its ground against scale-out all-flash NAS and local NVMe, since the retrieval seen here is at its fastest memory. Now, without mentioning brands, this particular scale-out NAS with SSD and hard disk is also very well known for its fast read capability. The next parameter we look at is the write mean latency. The mean latency for the small write is very good for the scale-out all-flash NAS and the local NVMe, which is less than 0.001 milliseconds. The scale-out NAS is much larger at 0.001 milliseconds. The mean latency for medium write is interesting. The scale-out NAS have lower latency than the scale all-flash NAS and came close with the local NVMe. Now, for write latency highest value, we can see that the general pattern from small write to large write, the most consistent performer is the local NVMe, followed by the scale all-flash NAS, and followed by the scale-out NAS. The gap between the two NVMe storage and the scale-out NAS can be almost 2 times larger. Now, it's very interesting that the write latency of the scale-out NAS for mid-size file are better than the scale all-flash NAS, especially in the 32 KB to 100 MB file size, where the bulk of the Gaussian read-write has taken place. Its last DIMM and local write on the cache is driving up the performance. However, the consistent and sustained performance of the NVMe are also fantastic. We are now looking at bandwidth. Now, although the mean is important, but the highest value achieved by the storage is more useful. But let's take a quick look at the mean bandwidth, right? The local NVMe has the best mean value at 0.024 MB, followed by the scale-out NAS at 0.022, and the scale-out all-flash NAS is around 0.019. I'm sorry, we cannot see very clearly the bar chart. Okay? For the mean bandwidth of medium and large read, the local NVMe, right, is ahead, followed by the scale-out NAS, and finally the scale-out all-flash NAS. For maximum bandwidth of small read, the local NVMe and scale-out all-flash have the highest bandwidth at 93 megabytes per second, followed by the scale-out NAS, which comes close at 78 megabytes per second. For the maximum bandwidth of medium and large file, the scale-out NAS is ahead, followed by the local NVMe's, and followed by the all-flash NAS. So in conclusion, we can see that it's not surprising that the scale-out NAS aggregated the bandwidth of all its storage nodes, and its aggregated storage nodes are larger than local NVMe and the scale-out all-flash NAS. For the write mean bandwidth, the local NVMe, right, have the best mean write bandwidth across all file size spectrums, followed by the scale-out NAS, and then the scale all-flash NAS is a near third. Again, although the mean is important, the highest value achieved by the storage is more useful, as we shall see. For the highest bandwidth for small write, the local NVMe, right, is the best at 118 megabytes per second. The scale-out all-flash NAS is around 60 megabytes per second, and the scale-out NAS come the closest at 45 megabytes per second. The highest bandwidth for medium read 32 KB to 10 MB, the scale-out NAS is best at 509 megabytes per second, followed closely by the local NVMe at 482 megabytes per second, and the scale-out all-flash NAS is around 464 megabytes per second. The mean bandwidth of large reads 100 megabytes and above. The local NVMe, the scale-out NAS, and the scale all-flash NAS were tied at 506 megabytes per second. So in conclusion, for bandwidth, the design of the storage is equally important to allow greater bandwidth for the entire storage. It's not just about which media the storage use. Now, each storage has its own strength and weakness in the matrix. But in the end, the most suitable storage subsystem for the application should be the one that provides the quickest processing time. As expected, the local NVMe is the fastest, completing the job in 32,208 seconds. The scale-out NAS comes second with 34,326 seconds, and the last is a scale all-flash NAS at 40,746 seconds. I would like to emphasize again that this is an observation only, and the finding is not conclusive as we have just installed Altair Mistral, and the time window to do a better averaging is not possible. Secondly, the storage subsystem is not an apple-to-apple comparison. The scale NAS is a fairly large system with lots of DIMM, SSD, and hard disks occupying several U's in the rack and have massive aggregated bandwidth, while the scale-out all-flash NAS is only a single chassis. In fact, the scale-out all-flash NAS is holding very well given its size, specification, and cost. But the observation, at least for me, is that a hybrid architecture with different storage medium and good L3 cache could be more performance and cost effective than if we focus on a single medium only, especially if the OS is able to utilize the various strengths of each storage medium. Number two, the file system, they are able to utilize and store data at the local drive at the compute level. By using a global namespace like the parallel file system is going to produce a higher performance. But you will definitely need good engineers to support the operation. Lastly, We need to do this metric collection for more applications so that we can turn this information into matching the right jobs with the right resources and hence bringing more value and performance for the applications. I thought it would be nice just to take a quick look at the Altair Mistral dashboard. There are three main selections: job I/O detail, system overview, system performance. Now, when we click the Mistral job I/O detail dashboard, we have an overview of the file system write information, including throughput, seek, count of the job. And the data are presented as the job run, giving the user and administrator a clear overview. Now, this is a continuation of the same dashboard. Here's a screenshot for the file system read, count, throughput for several file size as the job run. Again, very cleanly presented. Now, when we click the Mistral System Overview dashboard, we are taking a look from the system perspective, such as the various mount point, the bandwidth, etc. Sometimes you may be using different mount points, right, for the application, and you can have the information you need in a single dashboard. Here we have a glimpse into the memory use, right? The process virtual size, CPU time, right? From the memory section, we notice that the application is taking on an average of less than 1 gigabyte of RAM during the run. We also have information on the total CPU here, right? All clearly presented in a single page. When we click Mistral System Performance Dashboard, we are taking a look at the read-write latency as the job run. We can see that there are more data captured from the medium latency than the small and the large read. Again, it's very informative for people who want to study the I/O profile of the application. Now, overall, Altair Mistral have delivered what we really wanted from I/O profiling application and even more. But if there's one suggestion for Altair Mistral, if they, at least for myself, is that they could allow us to print the report directly from the dashboard. It will be fantastic for administrators. This is the last slide. Hooray! Now, a good product is not just having a good software, but more importantly, a good supporting engineering team. Mr. Manjuna from Altair have raised the bar of what is truly personal and professional support for customers like HPCC. I would like to thank Mr. Manjuna from Altair, who has taken so much time to support us in the use of several Altair products in Singapore. The handsome and capable man is on the photo here. With that, I end my presentation. Thank you.